Greetings once again. We are about to finish up Unit 9 and begin Unit 10. Unit 9 was dealing with oscillations, and we had a lot to say about simple harmonic motion. I just have a few more words to say about that before we move on to Unit 10, in which we will be discussing waves. So last time I mentioned that in addition to oscillations being damped, they can also be driven. And if they are driven in such a way that the frequency of that driving force matches the natural frequency of the simple harmonic oscillator, then you can achieve a condition known as resonance, in which the effect will be to maximize the efficiency of the energy transfer to the system. I encouraged you to take a look at this link, and hopefully you've already done that. If you haven't yet done that, I would say go for it. But what do all of these words mean? A simple example of resonance you've probably experienced at the playground as a child. If you treat someone swinging on a swing at the playground like a simple pendulum, then it will have some sort of natural frequency related to what we had discussed before with omega, where we have square root of g over L. And so this natural frequency will depend upon the length of your swing. And so you can drive that oscillator by pushing someone on the swing at a frequency that matches this frequency. If you apply this force and this push at that particular frequency, which you can usually tell and time appropriately, then you achieve, as we were saying, the most efficient energy transfer, which is basically to say that you create a large amplitude motion of the person on the swing compared to just a regular oscillation. Okay, so that basically wraps up Unit 9 for us, and we are going to move on now to Unit 10 and start discussing waves. In order to discuss waves, we want to make some definitions here, define some terminology. First of all, what do we mean by waves? Wave motion is a kind of motion which transports energy but not matter. So some examples of waves could be ripples on a pond, sound waves, waves on a string, and so on. We can also define something known as the wave speed, which describes how fast the disturbance moves through the medium. That wave speed is equated to it's related to both the frequency and the frequency and the wavelength of the wave. It's proportional to both. So the product of the frequency times the wavelength will give you the wave speed. That's sensible because a frequency has units of hertz, which is 1 over a second, and a wavelength lambda will have units of meters, so we get a meter per second here, and this product turns out to be the wave speed. There are different types of waves. Two common types of waves that we're going to encounter are longitudinal waves and transverse waves. The main distinction between the two is where is the disturbance compared to the direction of travel. What I mean by that is that transverse waves are waves in which the disturbance is perpendicular to the direction of travel. So if the direction of travel of the wave, say down this slinky, is this direction, you see that the disturbance is perpendicular to that. Some examples of transverse waves include light waves, waves on a string, S waves that tell us something about geological activity, and so on. So for a transverse wave, the distance between adjacent peaks, from peak to peak, or from trough to trough, or from any one point in the oscillation to the next identical point in the oscillation, is what we would call the wavelength. And as I was describing before, the vibrations or the disturbance is perpendicular to the direction of the wave. Now let's contrast that with longitudinal waves. Longitudinal waves are waves in which the disturbance is in the same direction as the direction of travel, parallel to the direction of travel. So here you see some compression taking place as the slinky as the disturbance is moving this way. The disturbance is in the same direction as the way that it is traveling. And so you can think about these as regions which are compressed uh, and regions which are spread apart, sometimes called rarefactions. So the prime example of a longitudinal wave that we're going to deal with is sound waves. Sound waves basically consist of areas of compressed particles. Typically air is where we're hearing sound waves, and then areas where the air is more spread out, and it's like a pressure wave in that sense, where there is a lot of molecules lined up and scrunched up here, and then rarefaction where they're spread out here, and that alternates as it propagates through space. So for a longitudinal wave, the wavelength will now be the distance between either successive compressions or successive rarefactions, or any one identical point and the next identical point. Now, waves can do a number of different things. One of the things that they can do is interfere with one another if there are more than one of them. This occurs by the principle of superposition, where the effect, the combined effect, is basically to add up the disturbance from one wave plus another wave if they coincide in space. So if you have waves lined up in such a way that each peak corresponds to another peak, so that their peaks are lined up and their troughs are lined up, which, by the way, is only going to happen if the frequency is the same. Nevertheless, if you have that condition, then you have effectively a double wave or a reinforced wave, which we would call constructive interference. On the other hand, if you have a wave where the peak lines up with a trough and the trough lines up with a peak, then you're effectively canceling the wave out, and we would call this destructive interference. So we can see this in light patterns, in ripple patterns. For light, when this occurs, we might think about it as a bright spot where there is constructive interference and a dark spot where there is destructive interference, and these are corresponding to where the intensity of the wave is at its maximum and minimum. Another thing that waves can do is that if we have a wave, for example, on a string, we can produce something called a standing wave. So here is a picture of a couple standing waves, and often when I do this in the classroom, I will have an actual rope like this that we shake, and the faster I shake it, the more I can get different shapes like this. What's happening is that instead of propagating through space, it's as if the wave is standing still. We still have the disturbance perpendicular, but it's standing still, so to speak. And we have some areas where there is maximal displacement from the equilibrium position, and then we have some areas where there is no displacement whatsoever. These areas that have no displacement, such as here, 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 are what we would call nodes. The places where there is maximum displacement are called what we would call antinodes. And so the faster that you would shake this rope, the more nodes and antinodes you produce. Examples of standing waves occur often in musical instruments. So a air column of a standing wave may be set up in a trumpet, or the waves on a string like a stringed instrument, produce standing waves as well. While we're on the subject of stringed instruments, why don't we discuss for a moment, take a diversion into the world of musical instruments and discuss the velocity of the wave on this string. So here's an equation for you of the velocity of a wave on a string, and it has to do with the tension that is on the string and also the mass density of the string. So the more tension we put on the string, the faster it will vibrate, and the more mass density that the string has, or the heavier it is, the slower it will vibrate. And that all seems rather sensible. We can go a step further and we can talk about the frequency of the wave on the string. In the musical world, we're going to call this the fundamental frequency. There are overtones to this frequency that we're not going to go into, but this is the main frequency that you will hear, the lowest frequency that you will hear. And so it can be found by taking this wave speed and dividing by twice the length of the string. So plugging in what we found for the what I gave you for the wave speed in the previous slide, this tells us that the fundamental frequency is given by this relationship here. And so the longer the string, then I increase this denominator, which decreases the overall number for the frequency, so I get a lower frequency. And that makes sense if you think about the fact that, say, a huge string bass with a very long string will produce low-pitched frequency sounds compared to a small violin with a smaller, less long string here, and it will give us then higher frequency, higher pitched sounds. So if we have a stringed instrument in which we need to actually fix the pitch and tune the pitch, then we're usually dealing with this by the tuning pegs, which adjust the tension on the string. And so, for example, a violin's A string should have, if it's in tune, a frequency of 440 hertz. And so in this example, we want to know if the string has this length, by what factor will the frequency change if I double the tension on the string? So let's go back to this equation that we had before, which was that the frequency is going to be 1 over twice the length times the square root of tension over mass density. Now in the tuning process, we are not changing the length of the string from end pin to bridge, nor are we changing the mass density of the string. The only thing we're changing is the tension. So if the tension is going to twice of what it was before, that gets square rooted when we plug it into this equation. So that tells me that the frequency goes to square root of 2 times the original frequency that we had before we increased the tension. And the square root of 2 is approximately 1.4 times that frequency. Okay, and that corresponds to choice A here. Also, I would like to point out that there's a similar instrument to violin that most people tend to forget about, and it's called a viola. 3 of the 4 strings on a viola are the same pitch as 3 of the 4 strings on a violin, and so there's a lot of overlap. And indeed, a violin's A string, which we mentioned having to be tuned to a frequency of 440 hertz, should be tuned to the same pitch for a viola. Nevertheless, the viola is longer than the violin, and so as such, we're going to have a different tension on the viola than what we had on the violin in order to achieve the same pitch. So we want to compare what those tensions are relative to one another. So let's go back to this equation once again. And what I'm going to do is I'm going to look at the ratio of the frequency on the violin to the frequency on the viola. This ratio is going to turn out to be 1 because they are the same, but I'm basically going to take this equation and divide one by the other. So 1 over 2L for the violin times the tension on the violin over the mass density. All this is going to be divided by the same thing for the viola. Now I am making an assumption here that the mass density of the two strings are the same. That may not be strictly true, but we will approximate it as such for this problem. So these mass densities will cancel, these 2's will cancel, this whole thing equals 1 because these also cancel. So what that's telling me then is that 1 is going to be equal to the length of the viola string over the length of the violin string times the square root of the ratio of the tensions here. Okay, solving this then for the tension on the viola, this should be the ratio of the lengths of the strings all squared times the tension on the violin string. So if I plug in what's given to me here, which is 0.325 meters for the violin and 0.37 meters for the viola, then I should find that the tension on the viola is going to be 1.3 times the tension on the violin. Okay, we will do more with musical sounds and waves in the next lecture.